Welcome to the extraction, acid-base reactions, and buffer solutions experiment. In this experiment, we are going to extract cyanidin 3-O-glucoside from red cabbage. We call it red cabbage even though it looks purple for a reason I do not know. In the first step, we are going to weigh out about 15 grams of the red cabbage. We're going to tear into relatively small pieces so that we can fit it in the weigh boat. On the scale, we zeroed the weigh boat, so we put the weigh boat on the scale, press the 0 button. That way, once we add the cabbage, we're assessing the weight of the red cabbage that was added. The goal of the first part of this is to extract the cyanidin 3-O-glucoside from the peel, and that cyanidin 3-O-glucoside is soluble in water. So we have a solution of water heating up on a hot plate. We're going to break those cabbage pieces into slightly smaller pieces so we have more surface area exposed so that molecule can dissolve into aqueous solution. And now you can see the solution starting to turn a little bit purple, and that means that we have our cyanidin 3-O-glucoside dissolving in that aqueous solution. Now the solution is turning even more purple, which means less of that cyanidin 3-O-glucoside is in the peel and more of it is in the solution, which means that we can isolate the solution from the red cabbage peel. That red cabbage peel is going to be slightly less red/purple because our cyanidin 3-O-glucoside is purple in color and we have now extracted it from the peel. We're isolating it from the peel by decanting. Another way to do this would be vac filtration, where we could actually separate the peel from the solution, but decanting is a little bit easier and faster, and since those cabbage peel portions are so large, it's very easy to separate the water from that. At this point, we can make our small library of references. So we're going to add some of this red cabbage to test tubes 1 through 6. Hello everyone, I just wanted to hop in and say hello. So when looking at the set of red cabbage solutions we made, we need to think about this on a molecular level. So for the cyanidin 3-O-glucoside, that is this molecule right here. On your worksheet, you have been presented with cyanidin 3-O-glucoside in its neutral form, which is what this structure is right here, its basic form, which is what this structure is right here, and its acidic form, or protonated form, which is what this structure is right here. So now that we have our set of 6 cyanidin 3-O-glucoside solutions, we're going to be adding strong bases all the way up to strong acids to the solution and see what color change results. On a molecular level, what's happening is that our strong acid is going to protonate the neutral form of cyanidin 3-O-glucoside, and a strong base is going to deprotonate the neutral form of cyanidin 3-O-glucoside. So the first thing we're going to do is add hydrochloric acid. So this is cyanidin 3-O-glucoside in its neutral form. If we add a strong acid to that, we're going to go from its neutral form to its acidic form. And for hydrochloric acid, that means that we're going to take that acidic proton and it's going to be added somewhere to this molecule. Now, looking at the conjugate acid of this structure, this compound here, which is the conjugate acid of cyanidin 3-O-glucoside, it looks like we have a positive charge on the oxygen. So that is different between this structure and this structure. It looks like a lot of double bonds moved around, and for the added hydrogen, that hydrogen looks the same, that looks the same, all these in the sugar look the same, that's the same. Okay, that alcohol functional group formed where before it was a ketone. So the proton is going to be added to the oxygen. So thinking about the arrow pushing mechanism to get there. We've got a lone pair of electrons on this ketone functional group. These electrons are going to take this proton. We're going to attack with our electrons and take that proton, and then we're going to break this bond, and those electrons are going to go to the conjugate base, which is our chloride anion. That gets us almost to this structure. We've added the proton there, but our charge, I don't think, moved that far. So in drawing the conjugate acid of this structure, all we need to do is draw a bond from the oxygen and put a plus charge on that oxygen, and that gets us to the conjugate acid. So rather than drawing this whole thing out within the video, I've already drawn it here. Let me drag that up and place it right there. So that is the conjugate acid of the arrow pushing mechanism that I drew. This lone pair of electrons is no longer on that oxygen. Instead of being a lone pair of electrons there, that is now that single bond. We have one lone pair of electrons left, which is optional to draw if you want. That lone pair is still there. When you count the number of electrons around the oxygen, we have 3 within the bonds, and the lone pair, which is 2, so that's 5 total electrons. Oxygen needs 6 to be neutral. So that is the conjugate acid of this acid-base reaction. Now, this structure here is remarkably similar to this structure. This is a resonance contributor of that. So if we're looking for how we get to this resonance contributor, we could move these electrons here. That'll neutralize the positive charge on the oxygen. We need to neutralize the positive charge on that carbon there by moving that double bond from bond to bond. And this double bond needs to go from bond to bond. And now my lone pair of electrons on the oxygen can go from atom to bond to get us to our double bond. So the conjugate acid, if we add a strong acid like hydrochloric acid, will fully form. So all of the cyanide 3-O-glucoside will be fully converted to this conjugate acid. So looking at the experiment, we're adding hydrochloric acid. So hydrochloric acid is the HCl to our cyanide 3-O-glucoside in its neutral form, and you can see that now essentially that purple color is all turning red, which means that all of our cyanide 3-O-glucoside is being fully protonated to form the conjugate acid of that. And there's the red color. Now in the next step we're adding a slightly weaker acid. So in that case we're adding acetic acid. So for the molecular structure for acetic acid, we have a carboxylic acid functional group. When we add this, it's still turning red, but I think that all of the equivalents of acetic acid are not being deprotonated. So if you're asked to draw the arrow pushing mechanism, it'd be remarkably similar to what we drew with hydrochloric acid. We'd show that those electrons are going to take that proton, and we're going to get to the same conjugate acid. But when we think about that arrow there, we're actually not fully converting. We actually have now an equilibrium balance between the two, the base and the conjugate acid. In the experiment now, we're adding water, and it shouldn't be a surprise that water will not be a strong enough acid to protonate or a strong enough base to deprotonate our cyanide 3-O-glucoside. Therefore, we basically are just slightly diluting the solution, making it slightly less purple in color, but not changing the color at all. Next, we have a weak base, sodium bicarbonate, which is going to partially deprotonate our cyanide 3-O-glucoside. Again, with that, we have an equilibrium balance where we have some of the deprotonated product and some of the cyanide 3-O-glucoside in its original form. So now we've added a slightly stronger base. We're going to deprotonate a little bit more of the percentage of our original starting material. And finally, we're adding a very strong base, sodium hydroxide. So once sodium hydroxide is added to this, we've got our 3 lone pairs of electrons. Sodium has a plus charge, oxygen has a negative charge. That's going to take this proton. We're going to deprotonate that, and that will actually take us right to our product. So we don't need to worry about the resonance contributors. Now this has multiple resonance contributors, so we could have shown a different form of this, but for convenience sake, all we need to do is take that proton, and we can form the conjugate base, and the conjugate acid water is in solution as well, and that turns it a green color. Now this is interesting, actually. We probably needed to add a couple more equivalents of sodium hydroxide, a few more moles of sodium hydroxide to fully deprotonate it, because our cyanogen 3O glucoside, once this is fully deprotonated, if we had all of this in solution, that'd actually be yellow in color. So really we're missing the last example, and that probably would be sodium hydroxide in a slightly higher concentration to show all of our cyanogen 3O glucoside fully deprotonated. Now that we have our reference library where we know the approximate pH of test tubes 1 through 6 based on the compound that we added to it, whether that was a strong acid, a weak acid, nothing, or neutral like water, or a weak base like test tubes 4 and 5, or a strong base like test tube 6, we added those so we have a library to compare to our unknown samples. The first thing we need to do is prepare our red cabbage solution before we add those unknown samples in. So we're filling about 5 milliliters of red cabbage solution into test tubes A, B, and C to test unknowns A, B, and C. So right now we're mixing unknown A into test tube A so we can predict the approximate pH of those unknown solutions. So for test tube A, it looks like I don't see a blue test tube in my mix, but I think that color between purple and green is probably that. So I'm going to guess the pH is somewhere between test tube 3 and 4, and from the reference table that we saw a little bit ago, as well as on your worksheet, you should be able to predict the approximate pH of the unknown A. For unknown B, that matches up a little bit more close to some of the test tubes that we have. And unknown C looks like it's also in the middle of 1 or 2 of those test tubes. As you're watching these videos, it's always helpful to have your worksheet out. So right now we're to the point where you can estimate the approximate pH values of the unknown compounds when dissolved in solution. For the last part of the experiment, we're making our buffer solutions. In test tube 10, we're adding sodium acetate as well as acetic acid. So for that experiment, we are adding 0.41 grams of sodium acetate into a 5 milliliter solution of 1 molar acetic acid. You could calculate the number of moles of each of those, which you're asked to later to do in the worksheet, and you'll find that the number of moles of sodium acetate equals the number of moles of acetic acid. So in that case, we have an equal amount of acid and base, so that is our buffer solution. In test tube 11, we only have acetic acid. So if we just have acetic acid, that has an opportunity to buffer added base, but it would not buffer added acid to that solution. So now we're adding our 5 milliliters of 1 molar acetic acid to test tube 11. And for test tube 12, we're just adding 5 milliliters of water. And now for all of these solutions, we're adding about 3 milliliters of indicator to each one. So it looks like for our 1 molar mix of sodium acetate and acetic acid, we're close to neutral but slightly more basic, which makes sense when you've got acetic acid and sodium acetate in equilibrium. The pH of that aqueous solution should be just less than 7. For the solution where we only have acetic acid, it makes sense that's even going to be more acidic, which you can see it's a much more pink color than the actual buffer solution. So that's just a solution of acetic acid. And for our solution of water, we expect our red cabbage solution essentially to just be diluted. And that still looks purple in color. So it looks like our red cabbage solution has just been partially diluted. For this test, we're going to add 3 drops of 10 molar sodium hydroxide, so a very strong base to each solution, and see what happens. So for our first buffer solution, when we have an equal amount of acid and base, we have that sodium hydroxide. It looks like minimal change. So I would say overall that color looks to be about the same as it was before. For the second test tube, in that case we only had acetic acid, so that acetic acid is going to be partially deprotonated by sodium hydroxide. It looks like it's slightly more basic. Okay, now that we're in equilibrium, it looks like it's gone to just about neutral. And then for the last one, where we only had water in the indicator, 3 drops of sodium hydroxide immediately turned that green. So that's a basic solution for test tube number 12. All right, 3 more drops of sodium hydroxide. Test tube 10, once we shake that up, it looks like it's still about the same as it was before, so it looks like our buffer capacity is still working. Our solution has not turned basic. Our equal amount of acetic acid and sodium acetate have resisted any type of change in pH thus far. All right, 2 more drops of sodium hydroxide. Still minimal change, minimal if any. All right, and then a couple more drops. We're definitely leaning a little bit more to the bluish purple area at this point. Okay, and then it looks like after a few more drops after that, now we finally got that test tube to be basic. So the buffer solution did pretty well. It resisted that change in pH for a while. Specifically, all of the acetic acid was being deprotonated. And instead of changing the overall pH of the solution, we just increased our concentration of sodium acetate. For the next, when we had a high concentration of acetic acid, this is acting as a buffer solution. It looks like it's pretty much tied so far with the other one. Okay, now it's slowly starting to turn. Nope, still not basic yet. So this is actually doing better than test tube 10. And remember, we only had acetic acid in that solution. So it wasn't an equal mix of both. we only had acetic acid, so that was essentially being deprotonated to make a buffer solution. Then we had a buffer solution, and it was still resisting changes in pH. And now that test tube 11 is still not quite as basic as the other two test tubes. So it looks like test tube 11 was our strongest buffer solution overall for this specific application.